Usually, when we talk about a medical diagnosis, or really any kind of scientific measurement, there is this, I don't know, this heavy expectation of precision.
Right. It feels like engineering.
Exactly. Like you break your arm, the X-ray machine spits out an image with that jagged white line, and the doctor just points at it.
It's binary. I mean, the bone is broken or it isn't.
Broken or not broken. It's clean, it's visible, and we can all agree on the reality of that jagged line.
And that kind of clarity is, incredibly comforting. We like things to be easily categorized, especially when those things dictate the very next steps in our lives.
But then you step out of the hospital and into the world of artificial intelligence, specifically algorithms that make decisions about our lives, and suddenly that X-ray machine is just, well, it's broken.
Completely broken. You're operating in a diagnostic landscape that is entirely murky.
Yeah. So welcome to this deep dive. Today, for everyone listening, we are taking on a massive, complex mission. We're unpacking the deeply human realities that are hiding right beneath the surface of machine learning and algorithmic fairness.
It's such a huge topic.
It really is. I mean, we are talking about the code that governs who gets a house, who gets a job, and the biases that quietly weave their way into that code.
And it's a vital exploration because it forces us to look past the shiny, futuristic veneer of AI. We have to confront something much older and much more uncomfortable about the architecture of our society.
Right, right. And to really understand what's at stake here, we have to ground this in reality. So I want you to picture a young woman. Let's call her Maya.
Okay.
She's 26 years old. She's a nursing student. And she is not just coasting through school. Maya has been working 3 different jobs just to put herself through her medical program.
Which immediately establishes a baseline for her character, right?
Right.
You're looking at immense resilience and, honestly, an undeniable work ethic.
The ultimate sheer determination. So Maya decides she wants to take all that drive and apply it to her community. She applies for a small business loan because her dream is to open a community clinic in a historically underserved neighborhood.
A great premise on paper.
Yeah. She submits her application, and a machine, literally a piece of software she has never seen, sitting on a server farm hundreds of miles away, a machine that has certainly never looked her in the eyes, says no.
Just a flat binary rejection, a 0 instead of a 1.
And here's the thing that really gets me, and it is the absolute core of our deep dive today. Maya wasn't rejected because she had terrible credit.
Right.
She wasn't rejected because her business plan for this clinic was poorly researched or, financially unviable. She was rejected because of a pattern buried deep inside a system built by people who probably never stopped to ask themselves how their math might inadvertently hurt someone exactly like her.
It's devastating.
Okay, let's unpack this. We built artificial intelligence, supposedly, to be better than us. We built it to be faster, perfectly consistent, free from human grudges, free from the tiredness and the bad moods that make human judgment so notoriously flawed.
Mm-hmm.
So how does a machine, a thing made of silicon and math, learn to discriminate?
Well, it is the great paradox of modern technology. The research on algorithmic fairness answers that question with a very sobering reality, which is that artificial intelligence does not invent its prejudices.
It doesn't invent them.
No, it inherits.
Inherits. Wow. Okay, so we aren't dealing with a machine suddenly developing an attitude problem. We're dealing with inheritance.
Precisely. I mean, we have this persistent, almost stubborn illusion that a computer is inherently objective simply because it uses mathematics to arrive at a conclusion.
Sure, because numbers are numbers.
Exactly. But every single data set that we feed into an artificial intelligence is fundamentally a mirror. It is a snapshot of the world exactly as it was when those data points were collected. And if the world we photographed was already unequal, if it already harbored historical biases and systemic exclusions, well, the reflection in that digital mirror is going to reproduce those exact same inequalities.
That completely reframes the entire concept of what a database is.
Yeah.
Like, we aren't just building a massive calculator.
No, we don't just build a tool, we built a memory.
A memory.
Yeah, we have constructed a vast digital memory of every unfair decision, every historical exclusion, and every quiet, insidious bias that lived in the data long before an algorithm was ever even written to process it.
That is chilling, honestly.
And think about what happens when that memory is put in charge of the future. When it decides who gets a loan, like Maya, or who gets an interview for a corporate job, or who gets flagged by a hospital for follow-up care, or even who gets a longer prison sentence.
Right.
The AI isn't just repeating history at that point. It is automating it.
It's taking history and scaling it up to an industrial level.
Yes. And worst of all, it makes that historical bias completely invisible. It hides it behind what researchers often call a wall of math. a wall of math.
Right. And that wall looks, to almost everyone, like a pure, unimpeachable objectivity.
Because if a human loan officer looks at Maya and says no, you might sense their prejudice in their tone. You might argue with them. You can ask for their manager, or you might even report them.
You have recourse.
Exactly. But if a computer spits out a proprietary score of 342 and the screen flashes application denied, well, the human instinct is to just assume the math is the truth.
Because you assume the math is neutral. Numbers don't have feelings.
Right.
But removing bias from AI is not merely some technical glitch to be patched in the next software update. It requires a fundamental restructuring of how we build these systems.
Yeah.
And our goal today is to walk through that blueprint, starting from the very foundation, to show you exactly how this hidden architecture works and, critically, what it actually takes to fix it.
Okay, so if AI is this mirror reflecting our past, what exactly are the mechanics of that reflection? Like, how does a machine look at historical data and learn what a good candidate is in the first place?
That's a perfect place to start. To understand Maya's loan rejection, we really have to look at the root of the bias. The uncomfortable truth that a lot of people in the tech industry are, frankly, still grappling with is that bias almost never starts in the algorithm itself. It starts in the data.
It is the raw material. Look, if you are baking a cake with spoiled milk, it doesn't matter if you have a state-of-the-art oven and a Michelin star chef writing the recipe.
The cake is going to make people sick.
Exactly. The algorithm is just the oven. The data is the ingredients.
Okay, let's explore a really fascinating example from the research on this. Imagine you are a machine learning engineer, and you are tasked with training an AI system to recognize what a successful corporate leader looks like.
Okay, pretty standard task.
Right. The goal is to build a tool that can scan headshots or video interviews and flag high-potential candidates. So you do what seems logical. You feed the machine 20 years of photographs and video footage from Fortune 500 boardrooms.
And, on the surface, if you don't think about it too deeply, that sounds perfectly rational. You want to identify successful leaders, so you build your baseline using the people who have empirically held leadership positions for the last 2 decades.
Right, but let's stop and think about the demographic makeup of those boardrooms over the last 20 to 30 years.
Yes.
They were overwhelmingly one gender, one race, and drawn from a very specific socioeconomic background. So the machine looks at thousands of these photos, processing billions of pixels. And it's like trying to teach someone what a musician looks like, but only showing them pictures of 18th century classical violinists.
That's a great analogy.
Like, the machine isn't maliciously ignoring jazz drummers or hip-hop producers or electronic artists. It's just doing math based on an entirely restricted worldview.
And we need to look at how the machine actually processes those pixels, because an algorithm doesn't understand the abstract concept of leadership.
It doesn't.
No, it doesn't know what vision or empathy or strategic thinking look like. It looks for visual correlations. So it scans those 20 years of boardroom photos and it finds the statistically dominant patterns.
Okay, like what?
Well, it might deduce that a successful leader is someone who wears a specific style of necktie.
Oh.
Or it might correlate gray hair with authority. It might even pick up on the specific lighting styles used in corporate portraiture from the late 90s.
Wait, really? So it's confusing the visual artifacts of the environment with the actual qualities of the person.
Exactly. It's confusing correlation with causation. The machine is doing exactly what the engineers asked it to do. It is succeeding at its mathematical task perfectly. We asked it to find the pattern in the data, and it found it.
But the pattern is flawed.
The tragedy is that the pattern it found was never a universal truth about leadership. The pattern was history's fingerprint.
History's fingerprint. I like that phrase. Meaning the historical realities of who was allowed into that boardroom, who had access to the Capitol, and who was systemically kept out.
Yes. The algorithm essentially learns that being a white male in a suit is a predictive feature of being a CEO.
Because mathematically, in that data set, it is.
Right. So when you show it a brilliant female candidate or a candidate of color, it scores them lower, not because it hates them, but because they mathematically deviate from the historical baseline it was fed.
Okay, so if the first real step in fixing this isn't writing a new line of code, it has to be conducting an audit of the data itself. Like, before you build a single model, you have to ask fundamental questions about the data set.
Absolutely.
You have to ask, who is missing from this database? Whose voice or image was never recorded? What decades-old decisions made by deeply flawed human institutions are quietly baked into these spreadsheets?
And that completely redefines the job description of a data scientist.
How so?
Well, you're asking someone who has spent years mastering Python, neural networks, and calculus to suddenly stop thinking like a mathematician and start thinking like a sociologist.
Man, I can imagine the friction there. You have an engineering team that wants to optimize for speed and accuracy, and now they're being told to act like historical detectives.
It creates massive friction. But for you listening, think about what this means in the context of whatever industry you work in. It requires technical teams to step completely out of their comfort zones. They have to investigate their own digital inheritance.
And that's not fun work.
It is incredibly uncomfortable work because
Yeah.
it often reveals that the data you thought was clean and objective is actually deeply contaminated by historical prejudice.
But it's necessary.
It is the absolute necessary price of entry.
Yeah.
If a team skips this step, if they just grab a massive data set off the internet and start training a model, they aren't building a neutral tool. They are just building a massive, highly efficient amplifier for the past.
A megaphone for historical prejudice. Okay, let's say a company does the right thing. The engineering team does the uncomfortable work. They act like sociologists, they look at their loan approval data from the last 30 years, and they realize, wow, this data is incredibly skewed against minority applicants.
Okay, step one complete.
Right, but what happens next? Because
Right.
we can't just throw out all historical data.
Right.
Then the AI has nothing to learn from.
Right, you can't start from absolute zero, no.
So we have to rebuild the reality that the machine learns from. If the data is a crooked mirror, we have to manufacture a flat one. This is about the architecture of reality.
I like how you put that.
Once you know where the systemic wound is, the treatment is rebuilding the data so it reflects the whole world, not just the historically privileged parts of it.
And that introduces one of the biggest logistical hurdles in the entire field of machine learning. Because rebuilding data is not just a math problem, it is a massive resource problem.
Okay, let me play devil's advocate here, or at least voice what I'm sure every startup founder and tech executive listening is thinking. Go for it.
Isn't it astronomically difficult, and more importantly, incredibly expensive, to go out and collect perfectly balanced representative data from scratch? I mean, there are massive open source data sets floating around the internet that anyone can download for free. If I'm trying to get a product to market, why shouldn't I just use what's easily available?
It's the most natural question in the business world,
Yeah.
and it is the exact trap that creates these catastrophic blind spots.
Okay.
Yes, building representative data is absolutely slower. Yes, it is far more expensive. But relying on free and convenient data is how you guarantee your system will fail the people who aren't represented in it.
Because it's a skewed mirror.
Exactly. The data lying around on the internet is basically a scrape of human history, and we just established that human history is biased.
So how do you actually rebuild it? What are the mechanical, technical solutions to counter this reliance on cheap data?
Well, it starts with a concept called representative sampling.
Instead of just scraping whatever data is easiest to find, you mathematically define the population your tool is going to affect, and you ensure your data set perfectly matches those demographics.
Walk me through how that works in practice. If a company realizes their data set is, say, 80% male and 20% female, what do they actually do?
It means the organization has to actively seek out the underrepresented voices. They have to open their wallets and pay to collect data from communities that history has traditionally ignored.
So literal field work.
Often, yes. It might mean sending researchers into different geographic areas or partnering with community organizations to gather fresh data. And in situations where you simply cannot gather enough natural data, you use a technique called oversampling.
Let's dig into oversampling. If I have a small group within my population, say a specific minority group in a rural area, they might naturally be drowned out by the sheer mathematical volume of the majority in a standard data set.
Right, because algorithms learn through repetition. If an algorithm sees 10,000 examples of Group A succeeding and only 50 examples of Group B succeeding, it might just dismiss Group B's successes as statistical noise.
Just a fluke.
Exactly. It won't learn the complex patterns that actually define Group B's behavior.
So oversampling means you intentionally amplify their presence in the training data.
But wait, I have a mechanical question there.
Sure.
If you just copy and paste those 50 examples of Group B 100 times so the numbers look balanced, aren't you just teaching the machine to memorize those exact 50 people? Doesn't that create a distorted, over-indexed reality?
That is exactly the danger, and it's why oversampling is so incredibly complex. You can't just duplicate the data rows because the model will overfit.
Overfit.
Yeah, overfitting means it memorizes the training data perfectly, but it fails completely when it sees a new, real-world example. It's like memorizing the answers to a practice test but not understanding the actual subject.
Ah, got it. So how do you avoid that?
Data scientists use synthetic data generation techniques. Okay.
One common method involves creating mathematical variations of the minority data points. You aren't just copying a profile, you are synthesizing slightly new profiles that share the core statistical attributes of the minority group.
So you're making up fake data that acts like the real data.
In a way, yes. You're essentially fleshing out the mathematical space they occupy so the machine can learn the boundaries of that group without just memorizing specific individuals.
That is fascinating. You are essentially generating a robust statistical reality for a group that was underrepresented in actual reality.
Exactly. You are adjusting the weights in the algorithm's learning process. You are telling the machine, pay extra attention when you see an example from this group, because they are rare, but their patterns are just as important to understand as the majority.
Man, well, the technical mechanics of that are brilliant. There is an emotional truth hiding inside this mathematical process. Every missing data point is a missing person.
That really reorients how you look at a spreadsheet, doesn't it?
It does. A missing row in a database isn't just a rounding error. It's a missing story. It's a missing chance to be seen accurately by a system that now possesses immense power over your life.
Right.
When you frame it like that, the financial cost of going out and doing the hard work of representative sampling doesn't seem so high anymore. It seems like the bare minimum of human decency.
Absolutely.
It's the only way a system can learn to treat a single mother living in a rural town with the exact same mathematical seriousness as a wealthy executive living in a major city.
Which brings us to an absolute non-negotiable rule for anyone managing these systems. Aggressive, transparent documentation.
Meaning what?
You have to document exactly who is and who is not represented in your data, and you must publish that documentation.
Why is publishing it so critical? I mean, shouldn't internal teams just handle it?
Because a dataset with unknown gaps is a dataset you cannot trust. Think about it. If you are a hospital buying a new AI diagnostic tool, you need to know if the data it was trained on included people of different ethnicities, because certain medical conditions present differently across demographics.
Oh, that makes sense.
Right. If the creator of the AI didn't document their data sources, they don't know who is missing. And if they don't know who is missing, they don't know who they are about to misdiagnose.
Okay, so let's assume the best case scenario so far. We've identified the bias in the historical data, and we've done the slow, expensive, but necessary work of rebuilding a representative data set. We've synthesized the data to protect minorities from being drowned out. The foundation is fixed.
Okay, a perfect foundation.
But, and this is a big but, even with a perfectly balanced data set, Maya might still get her loan rejected. And worse, when she gets rejected, she is met with a completely new kind of silence, the dreaded black box.
Yes. This is where we move from the data to the algorithm itself. And it tackles the concept of explainability, because you cannot fix or even challenge what you cannot see.
Right, because for years, AI systems were allowed to operate as impenetrable black boxes. We fed data in, a decision came out the other side, and nobody, not even the brilliant software engineers who coded the architecture of the system, could fully explain exactly how it weighted the variables to make that specific choice.
It's mind-boggling when you think about it.
Imagine the profound lack of power Maya feels in that moment. She's denied a life-changing loan, and when she asks why, the organization looks at her and says, well, the computer decided, and we don't really know exactly how it arrived at that conclusion.
It is a profound abdication of responsibility. It's a new kind of silence, just dressed up as technological innovation. You are essentially telling a human being that their livelihood was derailed by a mathematical equation that is too complex for human comprehension.
Right. So modern responsible AI demands light. It forces the model to show its reasoning. But how does that actually work mechanically?
Right.
I know researchers use terms like feature attribution and decision trees, but those sound like pure jargon to most people. How do we actually force a black box to explain itself?
Let's break down feature attribution, because it's one of the most powerful tools we have.
Okay.
Imagine an AI model is a massive committee of thousands of tiny advisors, each looking at one specific piece of Maya's application. One advisor looks at her income, another looks at her age, another looks at the fact she works 3 jobs.
Okay, I can picture that.
Feature attribution is a mathematical way of interrogating that committee after a decision is made to see which advisor yelled the loudest.
Huh. Okay, I like that. So how do you figure out who yelled the loudest?
Data scientists often use a concept drawn from cooperative game theory called shapely values.
Shapely value.
Yeah. Without getting bogged down in the deep calculus, the idea is that you calculate the model's output with a specific feature included, and then you calculate the output again with that feature removed or randomized.
Okay, so you're turning variables on and off.
Exactly. By doing this across thousands of different combinations of features, you can isolate exactly how much a single variable, say her zip code, contributed to the final rejection score.
So if the score drops drastically when you hide the zip code, you know the zip code was driving the decision.
Exactly. It quantifies the influence of every single input. And another method is using decision trees.
How did that differ?
Well, a deep neural network is wildly complex, but you can train a simpler, highly visual decision tree model to essentially mimic the behavior of the complex neural network.
Like a flowchart.
Precisely. The decision tree acts like a flowchart that a human can actually read. If income is above X, go left. If credit history is shorter than Y years, go right. It provides a human-readable approximation of the black box's logic.
But the method that really caught my attention when diving into this research is called counterfactual testing. I read about this and it honestly felt like a superpower. Walk me through the mechanics of a counterfactual test.
It is a brilliant auditing process. Counterfactual testing is essentially asking the machine an incredibly precise what-if question to audit its internal logic. You ask the system, would the outcome for this specific person change if we altered one isolated variable and kept literally everything else exactly the same?
So you take Maya's loan application, which was rejected.
Yeah.
You keep her income the same, you keep her 3 jobs the same, you keep her credit history exactly the same. And you ask the machine, what if Maya was a male?
Precisely. You isolate a single protected characteristic like race, gender, or age, and you run the simulation. If the machine suddenly approves the loan for the male version of Maya, you have absolute mathematical proof that the system is biased.
Wow.
You are forcing the AI to prove that it didn't quietly use a protected characteristic to make its decision.
But hold on, walk me through a challenge with that. We talked earlier about proxy variables.
Yes, proxies are tricky.
Right, because the machine doesn't always look explicitly at race or gender. It looks at proxies. If it looks at Maya's zip code or the high school she attended, those things are heavily correlated with race and socioeconomic status in the real world.
Right.
So how does counterfactual testing deal with the fact that these variables are so deeply entangled? You can't just flip her gender to male without addressing the fact that her environment might also be a proxy for gender or race.
That is the cutting edge of the challenge in explainability. And it's why counterfactual testing has to be incredibly sophisticated. You can't just flip one binary switch. You have to map the causal relationships between variables.
Causal relationships.
Yes. If you change a protected characteristic, you also have to mathematically adjust the downstream proxy variables that are causally linked to it. It requires building a causal model of the world, not just a correlative one.
That sounds incredibly hard.
It's extraordinarily difficult, but it is the only way to disentangle whether the algorithm relies on the fact that Maya works 3 jobs to show resilience, or whether it secretly penalized her zip code as a proxy for her background.
This makes an argument that goes way beyond computer science.
Yeah.
I mean, explainability is not just a technical feature or a debugging tool. It was fundamentally about human dignity.
It is entirely about dignity. Think about the difference in power dynamics. On one hand, you have a silent ruler, a system that dictates outcomes from on high without justification, leaving the person feeling helpless and erased.
Yeah.
On the other hand, you have a system that must answer to the public, that must mathematically justify its logic. When an algorithm can explain itself, when an institution can look at Maya and say, here are the exact 3 weighted reasons your application fell short, it respects the humanity of the person on the other end of the screen.
Right. It treats them as a citizen deserving of an answer, rather than just a data point to be processed and discarded. But, explaining a decision after the damage is done is only half the battle. Explaining it is great, but how do we stop it from happening in the first place?
Proactive testing.
Right. How do we know those choices are actually fair across millions of different scenarios before they hit the real world? That requires pushing the system to its breaking point before it ever goes live. This brings us to the endless stress test.
Test, break, and test again. That has to be the mantra of any responsible AI lab. And critically, this testing cannot just happen once, and it cannot just happen at the very end of development when everyone is tired and ready to launch the product.
When they just want to ship it.
Exactly.
Yeah.
It has to occur throughout the entire life cycle of the system.
There is a really jarring example in the research regarding a resume screening AI. Before deployment, engineering teams do this thing called bias auditing. They deliberately feed the model thousands of different scenarios to see how it reacts.
Standard practice.
Right. But researchers found that if you feed a resume screening AI two identical resumes, I mean, same education, same experience, same skills, but you name one candidate Emily and the other candidate Lakeisha, the AI routinely rates Emily higher.
And we have to be very clear about this to the listeners. That is not a glitch in the code.
It's wild because the immediate human reaction is, oh, the code is broken, we need to fix the bug. But the code is working perfectly. It's our society that's broken. And the code just learned how to replicate our flaws with stunning efficiency.
Right.
So if the code is just doing math, how do these teams actually measure fairness? How do you define a deeply philosophical concept like fairness to a machine that only understands numbers?
Well, you have to translate philosophy into a mathematical language. And researchers use a variety of complex metrics with names like equal opportunity, demographic parity, and predictive parity.
Okay, I want to really dive into these because I know they often conflict with each other. Let's start with demographic parity. What does that actually mean mechanically?
Demographic parity simply means that the outcomes of the AI should match the demographics of the population. If 50% of your applicants are female, then roughly 50% of the people who are approved for the loan or hired for the job should be female.
Okay, so it focuses entirely on equalizing the final outcome.
Yes.
That sounds perfectly fair on the surface. But what about predictive parity? How is that different?
Predictive parity focuses on the accuracy of the algorithm's predictions, regardless of the overall numbers. It asks, when the AI predicts that a candidate will be successful, is that prediction equally accurate for both men and women?
Give me an example.
So if the AI says a male applicant has an 80% chance of paying back a loan, and it says a female applicant has an 80% chance of paying back a loan, they both need to actually pay it back at an 80% rate in reality.
I see what you're saying, but help me understand the conflict here. Why can't a company just mandate that their AI achieves both demographic parity and predictive parity at the same time? Why is that mathematically impossible?
This is one of the most frustrating and fascinating realities of machine learning. It is often mathematically impossible to achieve both if the base rates of the two groups are different due to historical realities.
Walk me through a concrete example of that paradox.
Let's use credit scoring. Imagine two groups, Group A and Group B. Because of decades of systemic economic inequality, Group A, historically, has a higher rate of defaulting on loans than Group B.
Okay.
That is the unfortunate real-world base rate. Now, you train an AI to predict who will default. If you force the AI to achieve demographic parity, meaning it must approve exactly equal numbers of people from Group A and Group B, the AI will have to lower its standards for Group A to meet the quota.
Because there are naturally fewer traditionally qualified candidates in Group A due to the historical inequality.
Correct. But if it lowers its standards for Group A, its predictions will become wildly inaccurate for them. It will approve people in Group A who end up defaulting, which destroys your predictive parity.
Oh, wow. Okay.
Conversely, if you force the AI to maintain perfect predictive parity, meaning every person it approves has the exact same high probability of success, it will naturally approve fewer people from Group A, destroying your demographic parity.
Wow. So it's a mathematical seesaw. You push one side up, the other side inherently goes down.
Exactly. You cannot optimize for both simultaneously when the underlying reality is unequal.
So what does a data science team do? If you can't have both, who chooses?
Areas teams don't just pick one metric, get a green check mark, and say, we solve bias. They have to argue about the trade-offs. They have to decide which metric is more appropriate for the specific context of the tool they are building.
And who do they argue with? Just amongst themselves?
No, the consensus in responsible AI is that they must argue about these trade-offs honestly, out loud, and ideally in front of the people the system is actually going to affect. You have to explain to the public why you chose to optimize for predictive accuracy over a demographic outcome, or vice versa.
I love that image. Software engineers and data scientists having to justify their mathematical trade-offs to actual community members. But let's say they do all that. They balance the metrics, they make a thoughtful choice, they run the bias audits. Emily and Lakeisha are scoring equally. They launched the AI. They're done. They can go have a launch party and move on to the next project.
Absolutely not. The launch party is an illusion.
An illusion.
Yes. And this introduces one of the most insidious challenges in all of artificial intelligence. It's a phenomenon called model drift.
Model drift. Walk me through the